Good morning, good afternoon, good day, everyone, and welcome. We're about to start drilling down on EPA regulations. What is the latest buzz on pesticides and bees? Today's presenter is Anthony Melathopoulos, and he's an associate professor in pollinator health extension in the Department of Horticulture at Oregon State University, which was the first such position in the US. He's a pesticide educator, leads the master methodologist and bee steward programs in Oregon, and hosts a weekly podcast called Pollination. Anthony has been a member of NAPPC Pesticide Task Force since 2018. I'm going to turn this over to Anthony to start his session. Thank you, Anthony.
Thank you, Molly, and thank you to the Extension Foundation for hosting this webinar today. I'm going to launch a poll. I always hate these webinars because I can never see you. So just give me a sense of who you are. I'm going to launch a poll. Who are you? So if you don't mind just taking a second as I pull up my slides. Let's see who we got. Good, we got some pesticide educators here. Bee conservationists, wonderful. We have some beekeepers in the audience, welcome. And some homeowners, great. There we are. Okay, oops. All right. Okay, so I'm just ending. So we've got a lot of others. So maybe type in the, just quickly type in the chat who you others are. What would best describe you? That'll give me a sense of who I'm talking to today. And it's a really great mix, which I'm delighted with.
So Anthony, our participants can't use the chat. It's just about to let them know that they can use the Q&A feature down in the bottom row of Zoom.
Thanks, Molly. All right. Well, this is you guys. Oh, you guys can't see. So this is who you are. A great audience. I'm so excited. And I'm going to close that poll down. All right. It's gone, right? Fantastic. Well, today's presentation. So it's going to come out of my experience as working, as Molly mentioned, as an extension educator. I get hundreds of questions each year about whether or not a pesticide is safe to use around bees. And whenever I answer those questions, I'm always struck by the fact that most people don't realize that pesticides are already regulated to protect bees, and that most of their answers can be found on the labels that are affixed to each pesticide container. My goal today, it's modest, but I want to shed some light on the foundation of this regulation and bring you up to speed with recent changes to better ensure that pesticides that are sold on the market have minimal impacts to bees. Now, in doing so, I am joined, at least in spirit, although I see lots of people in the audience who are on the Pesticide Education Task Force of the North American Pollinator Protection Campaign. This presentation, in fact, came out of a series of discussions, or monthly discussions of the Pesticide Education Task Force, which I have been a member of since 2018. For those of you who don't know NAPPC, it's a collaborative body of more than 120 diverse partners dedicated to raising pollinator-related issues to the benefit of the health of all species of pollinators. It's been a center for this mission for over 22 years, and it has a tri-national scope: Mexico, Canada, and the United States. Now, the task force, of which there are 10 in total, represent cross-discipline, short-term project-oriented efforts designated to accomplish specific tasks. And the Pesticide Education Task Force is no different. It's worked on a number of projects, including a campaign to increase the reporting of bee kill incidences, working directly with the National Association of State Departments of Agriculture to disseminate best practices, as well as initiatives to guide gardeners, homeowners, growers, beekeepers, pesticide applicators to reduce the exposure of pesticides to pollinators. You can check out these many resources on the task force website and freely download them and put them out into the world. I'm going to have my email at the end of the presentation. You can email me for all the links that I talk about today. Here's me when I had hair. And my journey when I had hair as a pesticide educator came about through the Oregon legislature. In 2013, 2014, there was a series of 5 incidences associated with the application of an insecticide to linden trees in Oregon for the control of aphids that resulted in bumblebee deaths. The legislature wanted to prevent this from happening again, and they created my position to work across state agencies through an entity called the Oregon Bee Project on a comprehensive educational program for pesticide applicators on how to minimize impacts of pesticides to pollinators. This puts me on the road a fair bit. I'm going to be hitting the road shortly, and I see Casey Buell, our pesticide safety education program coordinator, on the call. And we train pesticide applicators specifically on how to read pesticide labels, and which has also resulted in a card that's produced and available from NAPSI, helping pesticide applicators understand pesticide labels. I give these cards out by the hundreds, and the purpose of the card is to help a pesticide applicator understand compulsory directions as well as advisory statements to minimize exposure to bees to pesticides. These instructions, as well as others designed to protect other organisms that pesticides are not targeting, are found on all pesticide labels. Now, the methods for reducing exposure outlined on pesticide labels are known as mitigations, and they're a critical tool for specifying how a pesticide that is toxic to bees can be used in a way that can significantly reduce its impacts. What I want to focus on today is the process by which a regulatory agency is able to assess a pesticide, translate it into a pesticide label that specifies how a pesticide should be used to ensure the full benefit of the product can be realized without negatively impacting one specific group of non-target organisms, the ones that I focus on, bees. But before we go too deep, and I know there's people who know this material real well and others who this is new to you, but let's get some basic terminology out of the way. When talking about pollinating insects, we often talk about insecticides. But if you pick up a newspaper, you'll see the word pesticides also used when talking about bees. So what's the difference? Pesticide is a general term. It refers to any substance or mixture of substances that's intended to destroy, repel, or prevent a pest or pathogen. Within pesticides, there are groups specific to the product is intended to target. 3 groups are relevant when we're talking about pollinating insects. Insecticides target insects, herbicides target weeds, and fungicides target pathogenic fungi. Okay, now that we got that out of the way, let's switch gears as I take a deep dive into how pesticides are regulated. First, let's talk about how risk of pesticides are assessed to bees by federal agencies. And in doing this, I want to make clear that state tribal agencies also have authority to regulate pesticides, but for the purpose of this talk, I'm going to focus at the federal level. I think to properly understand the foundation of pesticide regulation, we need to go back to the beginning. After all, pesticides weren't always subject to regulation. Pesticide regulation is a product of the progressive era of the 20th century. It emerged from circumstances that were really tangentially related to pesticides. One of the sparks surrounding the need for regulation were health violations and unsanitary practices in the U.S. meatpacking industry, which is highlighted in Upton Sinclair's 1906 novel, The Jungle. President Teddy Roosevelt famously branded Sinclair a crackpot, but the public discontents expressed through this book no doubt motivated Roosevelt to bring about the Pure Food and Drug Act of 1906. The act forbade foreign and interstate commerce in adulterated or fraudulently labeled food and drugs. This act had far-reaching powers, enabling government officials to seize condemned products for the market. Fresh, canned, or frozen food that were shipped across state lines had to have a label like this. Let's get it. There it is. On it. Just to be clear, the underlying motivation of this legislation was distant from the safety of bees, but really it becomes the foundation, even though it's about protecting consumers from fraudulent activity. It was this growing sensibility of protecting consumers that was at the heart of the first federal act regulating insecticides. The Insecticide Act of 1910 made sure that when somebody bought an insecticide, like this Pyrex product, it contained what the manufacturers promised. It also set purity standards and protected farmers from insecticides that were either ineffective or were dangerous to use. Again, this has nothing to do with bees or pollinators, but it set the stage for the federal government to regulate pesticides that were previously freely made, bought, and sold. The regulation of pesticides continued to evolve in the 1930s, culminating in a landmark piece of legislation that came in the wake of World War II, the Federal Insecticide, Fungicide, and Rodenticide Act of 1947. You, I'm sure, have heard someone at a meeting talking about pesticides and bees blurt out the acronym FIFRA, and this is what they're referring to. Key provisions in FIFRA have established the basis of pesticide regulation until the present. Importantly, FIFRA fundamentally recognizes pesticides as economic poisons, meaning the risks had to be balanced against the benefits to society they provided. This point of balancing benefits and risk, considered broadly, will be important when we consider risk to bees and how they're evaluated today. FIFRA also required the Department of Agriculture to register all pesticides prior to their introduction into the market. This process of a company registering a pesticide continues to the present. These pesticides also had to have warning labels that had to list the active or pesticidal ingredients. Again, this is something that continues up until the present. But unlike today, the law did not provide a basis for the federal government to remove a hazardous pesticide from the market. Many credit a second popular book, namely Rachel Carson's Silent Spring, for bringing about the change that authorized the USDA to be able to remove a pesticide from the market in the 1964 amendments to FIFRA. In the book, Carson outlined research that showed that a widely used insecticide, DDT, was bioaccumulating in the food chain, resulting in thinning eggs in raptors at the top of the food chain, most notably among bald eagles, our national symbol. It was under the authority of the 1964 amended FIFRA that the Secretary of Agriculture revoked the registration for all products containing DDT. It was the first of many pesticides to have their registrations canceled under the Act on the basis of unreasonable risks to the environment or human health, which were deemed to be too much to offset the benefits of using the product. As a consequence, these products are prohibited from being used in the United States. For our purposes, the second big change to FIFRA took place in the 1970s. In 1970, Congress transferred the administration of FIFRA to the newly formed Environmental Protection Agency, which you know as EPA. This marked a shift in the focus of pesticides to be reasonably safe, which is the defining problem that society demanded in the early 20th century, the issues that in Sinclair's Jungle, to the reduction of unreasonable risk to human health and the environment, the new concerns after World War II that are emblemized by Carson's Silent Spring. This new policy focus was expanded by the passage of the Federal Environmental Pesticide Control Act of 1972, which amended FIFRA. In addition to the goal of no unreasonable adverse effects to the environment, it also set timelines to review new science on already registered pesticides. Finally, it divided pesticides into those that are available to the public for purchase and use, which are known as general use pesticides, and those only available for sale to and used by a certified licensed pesticide applicator. These are known as restricted use pesticides. This last provision of the 1972 amendments to FIFRA is something that I want to underscore. The significance of restricted use pesticides is explained in detail by Dean Hertzfeld, who is a retired pesticide safety education program leader for Minnesota. I interviewed him on the Oregon State University podcast Pollination in episode 106. As he explains, with the formation of EPA's stricter standards, many pesticides would have to be canceled because they would have been deemed too hazardous. But these hazards were deemed by Congress to be something that could be minimized with additional education of certified or licensed pesticide applicators. Consequently, states required that these applicators study and pass exams before they use restricted use pesticides. And in many states, they can retain their certification if they take continuing education credits, like Oregon. I'm responsible for delivering training on pollinator protection, and there's a number of courses on pesticide safety. I've trained over 7,000 applicators in the state how to read the pesticide label to understand what kind of mitigation is necessary to protect bees. Consequently, this provision ensures that there's a tier of pesticide applicators who are trained to mitigate risk through comprehensive understanding of what pesticide labels mean in practical settings. Let me round out this introduction to pesticide regulation by reflecting on this history and noting how regulation is not a static process. Pesticide regulation has been continually evolving to reflect new science and emerging concerns within society. Effectively, the process of creating laws attempts to keep pace with emerging demands from society. If we know anything, the regulation of today will likely change to meet the unanticipated demands the future has in store for us. Bees certainly were not at the front of mind in 1910 or 1947, and even in 1972. It's a relatively new concern that started to become apparent in the 1980s, when beekeepers began to notice dead colonies after certain insecticide applications, and it became prominent in the 2010s. A robust regulatory system is one that can adapt to new challenges as they emerge, rather than one that's inflexible and unable to adapt. And when it comes to bees, the regulatory system has been flexible and has undergone a host of changes. If we take this is a short history of assessing adverse effects to bees beginning in the 1980s, in the wake of some of these early insecticide incidents, you'll see that over the past 30 years, EPA has required companies that register pesticides to supply data from laboratory and full field colony level studies to assess adverse effects to bees. This information helped determine whether a pesticide could be registered and if it required a statement on the pesticide label warning applicators of potential hazards. But in 2011, EPA issued a comprehensive interim guidance on additional acute and chronic toxicity studies of adult and larval bees, along with exposure studies in pollen and nectar with which to quantify risk to bees. This increased the amount of data on the effect of pesticides companies needed to provide to get a pesticide registered or re-registered. The final milestone I want to highlight came in 2014. Based on input from the EPA's FIFRA Scientific Advisory Panel, the agency, in collaboration with the California Department of Pesticide Regulation and Health Canada's Pest Management Regulatory Agency, released guidance on assessing pesticide risks to bees. I want to spend the rest of my time today trying to explain what has changed over 30 years, as I fear many of these changes have gone under the radar of many who are committed to protecting the health of bees, including many beekeepers. But before I do this, let me sum up the key points from this introduction. The key takeaway is that under FIFRA, no pesticide should have unreasonable adverse effects on the environment when used in accordance with the label. But the key word is reasonable, and what is reasonable must take into account the economic, social, and environmental benefits of the use of any pesticide, which I hope to have impressed on you is continually changing. Whew, that was a lot of history and laws. Okay, let me take a moment and back up to consider what risk means when it comes to bees and pesticides. In doing this, I'm going to be switching gears to consider the present and how EPA has demonstrated flexibility when confronted by increased concerns around the health of bees. Of course, public concern around bees has been prominent over the last decade, and perhaps one of the most galvanizing moments came in 2013 when a pesticide application in my home state of Oregon resulted in a series of significant bumblebee kills. Picture this. It's National Pollinator Week in Oregon. It's a time of year when a popular suburban shade tree, the linden or lime tree, comes into full bloom, as you can see in one of those pictures. Having a relatively open flower and coming into bloom at a time of year when nectar and pollen resources are starting to fade, it's visited by a whole range of bees. These trees also experience tremendous buildup of aphids that ooze sticky honeydew on sidewalks and parked cars below. A licensed certified pesticide applicator was called in to treat the aphids on the target parking lot with the insecticide product Safari fairly close to when the tree was in bloom. This resulted in one of the largest documented bumblebee kills ever, with an estimated 50,000 bumblebees dead in the parking lot, triggering national public concern. The Oregon Department of Agriculture acted really swiftly, amazingly. They wrapped all the trees in shade cloth, and they eventually worked through the Oregon legislature to restrict the use of similar products on linden trees. Notably, in this example, the insecticide label had warnings about the product being toxic to bees, which have spurred the efforts of myself as well as other members of the NAPSI task force to improve education to pesticide applicators through the pre-existing certification programs in each state. What I want to draw your attention to is that this was an example of an insecticide that was applied at a time when it should not have been, an example of a situation where there was a high risk of killing bees. So this term risk, it tells us the magnitude and likelihood of adverse effects to bees as a result of exposure to a pesticide treatment. We can state this differently. Risk is how likely a pesticide application is going to cause some bad effect. It can be outright death. It might be other sublethal effects. We can break this down further when we consider the linden tree example again. Risk is basically a product of two things. The first one should be obvious to you. Toxicity of the pesticide. A pesticide that is more toxic to bees will have a worse impact on the bees or a greater magnitude. But toxicity alone doesn't translate into risk. Consider this linden tree when it isn't in bloom. You won't find bees visiting and contacting the tree at this stage. It therefore has a small likelihood that bees will be exposed, making risk low. But what this assessment changes drastically when this linden tree comes into bloom. It literally hums with a wide array of bees. It is an amazing bee tree, across the nation. Exposure, though, with a pesticide applied at this time is very high. Situations where a pesticide that is toxic to bees is applied to a bee-attractive plant that is in bloom can result in a high likelihood that there'll be a very large adverse effect to bees. As you can imagine, this is a much more complicated process in real life. Individual bees have a range of sensitivities to pesticides. We know, for example, that genetic variation, age, or species of bee can vary in sensitivity to the same pesticide. Likewise, exposure varies by the environmental conditions when the pesticide is applied. How many times a bee exposes itself to the pesticide? For example, if it returns to the treated plant multiple times or just once. Guidelines for risk assessment are crafted in such a way as to estimate risk from data generated from the lab and field experiments in a manner that anticipates this variability inherent in such a complex and dynamic system. Let me move now to how this is done, the risk assessment process used at the Environmental Protection Agency. EPA estimates risk in the real and complex world from the snapshots of data that are provided when a pesticide is registered or reevaluated. Let me preface my remarks by stating this is a very complicated endeavor, and I will only be able to talk about the process in broad strokes. There's a lot of nuance in risk assessment that is really impossible for me to convey in the brief time we have here today. Fortunately, EPA has a fantastic page dedicated to the topic of risk assessment and pollinators. You can use that QR code on the screen to directly get to this page, or simply Google the term EPA, how we assess risk to pollinators. You can also email me at the end of the presentation. I have my email, and I'll be happy to get these to you. I also think excellent background on this topic can be found on YouTube in a webinar our EPA gave in 2020. I'd highly recommend this video, and you again can access it using this QR code. And there will be a recording of this video too, so you can go back for the QR codes. This problem of taking the complex life of bee exposure in the environment is tightly interwoven with the biology of the bees, as Fred Whitford from Purdue University expressed in episode 2013 of the Pollination Podcast. As Dr. says, EPA's approach to risk assessment is only understandable when considering bee biology. Oops, I'm gonna slide off. Oh, no, I'm not. This brings me to my third recommendation for resources, a publication from Dr. Whitford in the extension catalog that draws the parallel between EPA's data requirements in the biology of bees. I really recommend this publication as a starting point. It's written as extension's so good at in real basic language. Now, at the heart of this framework is a tiered process of assessing risk. This tiered approach is consistent with the more expansive framework that has been evolving within EPA under the broad umbrella of, it's called ecological risk assessment. It's sort of the broad umbrella used throughout the assessment of ecological risks. The key principle is that tests required to evaluate the effects on non-target organisms like bees are arranged in a hierarchical or tiered system, progressing from laboratory studies of individual bees to field-based studies of honeybee colonies into full field studies. The overall process is intended to identify those chemicals which are not considered likely to be an issue for bees and enables the agency to better allocate resources and testing to those chemicals which appear to be problematic. In broad strokes, as you move from tier 1 to tier 2 to tier 3, the determination of risk becomes increasingly refined as the data approaches field conditions. On the right, you can see a schematic of the decision points for assessing risk and requiring higher tier tests to refine estimates of risk. You can see it's way too complicated to trace each of these lines down from the top. But the point is that as you move from the boxes to the boxes and the arrows, there are decision points where additional data may or may not be needed to better characterize potential risks. If data are not available, then risk becomes more uncertain, and in the absence of data to the contrary, the agency might just presume risk. I know this graph is a lot, so I want to simplify each of the steps in piece. Tier 1 starts with the most basic question: are bees likely to be exposed? This involves understanding whether the crop may be attractive to bees, whether applications occur near bloom time, and the time at which compounds are applied. A key element is looking at the plants the pesticide is being proposed to be used on. Is this crop one where there's even a potential exposure to bees? To answer this question, EPA evaluates multiple lines of information, including the following USDA document that summarizes the attractiveness of crops to bees and whether it uses contracted pollination as part of its production. Even if a pesticide is not proposed for use on a pollinator attractive crop, EPA will still evaluate risk to bees that may be foraging adjacent to the treated crop. I hope you caught that. So even if that crop is not attractive, if there's a likelihood there's an adjacent crop where the pesticide could drift to, that's taken into account. Here's an example from the USDA, from that USDA guide I just showed you. The second line, sugarcane, for example, is neither attracted to honeybees, bumblebees, or solitary bees, which is indicated by that negative sign. Now let's look at another crop, the one on the third line. Sunflower. It has 2 plus signs indicating high attractiveness, including a listing of the generic names of the many species of solitary bees that visit sunflower. Moreover, the guide indicates whether managed pollinators are used to pollinate the crop. And in the case of sunflower, the answer is yes. Consequently, a pesticide being considered for sugarcane may be characterized as being of minimal risk to bees, whereas the same product being considered for uses on sunflower may require higher tier studies if risk estimates exceed the agency's level of concern and risk cannot be mitigated effectively through label language. Recall, however, as I mentioned earlier, if there's a likelihood of pesticide drift to a crop adjacent to sugarcane, testing might still be required to characterize risk. All of this information about attractiveness of crops is found in this USDA document, which is available online. If exposure is likely, then laboratory tests are required on the effects of the product on individual bees. This is the starting point for Tier 1 testing in the laboratory. Laboratory tests outlined in this table are required to test the effect of the product on individual bees. This table has a lot on it, so let me highlight a few key elements. Tier 1 tests include acute toxicity tests, where the bee is exposed once to a pesticide, as well as chronic tests, where the bee is exposed repeatedly over time. It involves tests of adult bees, as well as larval bees. Many of these tests also differentiate between the toxicity of whether the bee eats the pesticide or whether it physically contacts it. Now that's just Tier 1. Remember, all pesticides go through Tier 1. So if the crops that they are to be applied to are deemed to be attractive to bees, remember all the pesticides have to go through this. So how are these Tier 1 laboratories tests carried out? Here's an example of 2 of the tests. On the top panel, you can see an adult honeybee being dosed with a drop containing varying concentrations of pesticide in the acute contact toxicity test. On the bottom panel, you can see the chronic larval test, where a honeybee larva is fed a standard diet with varying amounts of pesticide. The larva develops over a 3-week period after the start of the test, allowing the toxicologist to view the effect across the entire developmental period of the bees. I want to point out that honeybees are used as a surrogate for other bees in these Tier 1 tests, in part due to their availability and the extent to which they're amenable to lab tests. This isn't to say EPA does not evaluate data on other bee species at the Tier 1 phase. I'm going to show you an example in a couple slides, but the bulk of these tests are done on honeybees. These tests are summarized in 2 ways. The test results will have these 2 acronyms, the one LD50, which is the amount of pesticide applied to a bee, which causes the death of 50% or 1/2 of a population of honeybees, and the no observable effect level, which stands for, which is the acronym is NOEL. So let's take a look at these 2 concepts. The toxicologist doing the test will note a range of impacts on bees, including sublethal effects. This might be changes in their behavior, but a key measurement is how many of the bees in the test population die. The summary for acute toxicity tests is frequently expressed as the dose that kills or is lethal to 50% of the test population. For chronic exposure tests, the data are often summarized in terms of the highest dose or level, where the pesticide has no observable adverse effects on the bee. This means the dose where the toxicologist can't discern a measurable difference between a treated bee and a bee that's untreated. Okay, here's a recent example from the risk assessment of a relatively new compound. It's a lot, but I wanted you to see the results of the different tier 1 tests for honeybees and how they're presented in a risk assessment document. Note as well that the risk assessment also includes an additional test here provided for bumblebees, the acute, contact, and oral test. Also note that you can see how they list under comments all the sublethal effects. For example, it was noted that when using this product, although at levels that didn't kill the bee, the consumption of syrup was impeded. So this is all included in the risk assessment. The next step is to take these test results and contextualize them with respect to how much of the pesticide the bee is likely to encounter in the field after application. Take, for example, this worker honeybee visiting white clover flowers, and if I can put a plug for my own state, leading producer of clover seed in the nation. And the beekeepers are key in this production. But the question is, how much of a pesticide is she likely to be exposed to by contacting the flowers and ingesting nectar and pollen? This is termed the estimated environmental concentration, or EEC. Here's the representation of how the data from one of these tests, the adult acute contact test, is shown, is summarized. The test results are put in context with the expected exposure a bee would come into contact with. The estimated environmental concentration, seen on the top there. But how on earth does one even estimate the amount of pesticide a bee would be exposed to in the environment without directly measuring it? EPA looks at what is being EPA looks at what is being proposed for application rates, the chemical properties of the pesticide, how much a bee is expected to consume in a day, and other factors, and then they come up with a worst-case scenario. This calculation is made for each route of exposure and for each crop that the pesticide is being registered for. If the risk quotient depicted here is above a level of concern, then further refinements are required to assess the risk of the pesticide. In contrast, if the risk quotient falls below the level of concern, then the pesticide may be characterized as being of minimal risk to bees. So let's say a pesticide had a contact LD50 to an adult honeybee of 10 micrograms per bee. That is to say, if a foraging bee picked up 10 millionth of a gram of pesticide on their bodies while foraging on a treated cherry orchard, 50% of them would likely die. But the amount of pesticide a foraging bee is expected to encounter is 0.1 micrograms. So the proposed application rate, 0.1 micrograms per bee for a proposed application rate and use pattern. This means risk quotient of 0.01. Since the threshold of concern is set at 0.4, this type of application may be characterized as minimal risk. If the same conclusion was arrived at for other modes of exposure. You might ask yourself, what does a level of concern of 0.4 even mean? Levels of concern are based in bee toxicology and are set at two levels. For acute exposure, when a bee is expected to contact the pesticide once, the level is set at 0.4, which is equivalent to 10% mortality expected as background mortality in a test. For scenarios where the bee is expected to repeatedly be exposed to the pesticide or chronic exposure, the level of concern is set at 1, which essentially equates the exposure level at the no observable effect level. In contrast, if the pesticide had a lower LD50, instead of 10 micrograms per bee, it was 500 times more toxic and had an LD50 of 0.2 micrograms per bee, it would exceed the 0.4 level of concern threshold, and the registrant may be required to provide additional data to further refine the characterization of the risk of that pesticide. A lot rides on the estimated environmental concentration. So to help refine what this exposure is, EPA may require the registrant of the pesticide to spray those cherry trees and collect samples of pollen and nectar to see if it is reflective of the actual estimates of environmental concerns in the environment. and to see if they are reasonable. Say, for example, rather than 10 micrograms for B, the actual amount a bee would encounter in the environment is much lower. This would suggest that the risk is even lower than the predicted initial Tier 1 estimate. Okay. Let's just, I guess I can't, yes, poll. I want to see how you guys are doing out there. I think I'm going to try and get a second poll going here. Oops, not that one. Here we go. Just in terms of what, I want to just make sure I haven't lost everybody. If you were to look at this statement, a Tier 1 characterizes risk only considers short-term effects. Tier 1 characterization of risk only considers short-term exposure of adult bees to a pesticide. Do you see that as true or false? True statement. Yes, Tier 1 characterizes only short-term exposure. Or false. No, it doesn't just consider short-term exposure, but also chronic or long-term exposure. Okay, I'm just going to end the poll, and I can see here that most of you got it. It is false. It does also consider chronic exposure. Thanks very much. Okay. In many cases, let me just move on. We've gone through Tier 1. It's deemed that we need more information. In many cases, you can't characterize risk at Tier 1. And so while measuring the residues on the nectar and pollen on sprayed plants might refine the characterization of risk, oftentimes refinement may require more testing of the pesticide under more realistic exposure scenarios. This means moving beyond the lab and individual bees into whole colony level evaluations of lethal and sublethal effects in semi-field or full field scenarios. Here's an example of a Tier 2 test. There's two examples here. One is you can see on the left is you provide a bee colony with a diet spiked with the pesticide at varying concentrations. But it also may be what you see on the right. You have an experiment where bees are restricted for foraging on anything but the treated plants, and you enclose the bees and the treated plants under a tunnel. There's also Tier 3 tests, which are even larger scale, where entire replicated fields are treated with pesticide and impacts on the colonies are measured. Yes. It's worth noting that increasing realism comes at a cost. Here are figures from Dr. Whitford's Complex Life of Bees. I hadn't seen figures like this before. It says that while the full array of Tier 2 semi-field tests may be 3 times that of Tier 1 lab tests, the full Tier 3 field trials are almost 10 times that of the Tier 2 tests. The tiered framework provides a way to keep costs down for testing pesticides that are relatively low risk to bees while providing full scrutiny of products where toxic impacts may be less clear. Clearly, for these tiered risk assessments to provide reliable risk characterization, the data that is collected must be collected in a robust manner. And it bears asking the question as to how the data for these studies are generated. Here's a detailed account of the approach to generating this data from 2 researchers from Canada who were involved in running a Tier 3 study for an insecticide used in canola blooming in the background. I know these researchers really well. Dr. Scott Dupree did her graduate work in my lab, where I got my master's, and Dr. Cutler was my PhD supervisor. Here's a refereed publication describing their Tier 3 study. Now, when you go down in the material and methods, you'll notice, here we are, the excerpt from the paper, in the first sentence that the research used good laboratory practices, which are described in 2 citations. You can see the 2 citations there. The citation references the Code of Federal Regulation, followed by a lot of numbers. So somehow, whatever data they generated was guided by the Code of Federal Regulations. I don't know about you. I actually didn't know what the Code of Federal Regulations was, so I looked it up. The Code of Federal Regulations codifies general and permanent rules that federal agencies like EPA have to adhere to. If we look more closely at what rules EPA has to adhere to, a key part is in Section 158. This part requires the pesticide applicants and registrants to generate data to support product registrations. These data requirements are specified in code. What it says is that pesticide companies have the responsibility to generate the data using good laboratory practices. Also, EPA sets guidelines for these tests, and we've seen these guidelines earlier in some of the Tier 1 tests. Those are described in specific guidelines. So what do good laboratory practices involve? Fortunately, Doctors Cutler and Scott Dupree wrote the following piece in the journal Bioscience describing their experience. In the introduction of the paper, they raised the question that I had, and I'm sure all of you are having. How can you trust the data provided by companies that are looking to sell a pesticide? The answer to this, an answer specified in law under the Code of Federal Regulations, are good laboratory practices. As Cutler and Dupree point out, the impetus for the development of good laboratory practices in the 70s was concern about the validity of the non-clinical safety data submitted to the Food and Drug Administration in the United States, stemming from incidents of the incompetent execution of studies, insufficient documentation of methods and results, and even outright fraud. As a consequence, good laboratory practice were developed as a way to ensure every step of the study was actively scrutinized during the experiment through the use of independent quality assurance personnel. As Cutler and Scott Dupree discovered, the quality assurance personnel are actively monitoring the research across all stages of the experiment. They noted that on several occasions in their study on canola, the quality assurance personnel identified transposition errors that occurred from data sheets to the electronic spreadsheet, as well as an ambiguous note recorded by technical staff, illustrating the thoroughness of this oversight. And just to conclude, I wanted to end on this account by Cutler and Scott Dupree of the extent to which third-party validation works independently of the people actually collecting the data. As they recounted, the quality assurance personnel would, on occasion, put on a bee suit and see how data was being collected and whether the integrity, consistency, and reproducibility of the data was being upheld. Let me conclude now with the point where the rubber hits the road. After the risk assessment is complete, the pesticide may only be registered under the provision that the pesticide applicator use the product using specific mitigations to ensure exposure to bees remains low. How is this communicated? All pesticide labels have a detailed label outlining how to use the pesticide safely. The label contains all kinds of specific information that is not conveyed by looking at the packaging. Take these two hypothetical pesticide products. They look very different, don't they? But in fact, they are the same pesticide marketed in two different ways. The instructions for using these products outlined on the pesticide label, in contrast, is identical. There's a lot of information on the label, but I just want to focus on the sections that are relevant to protecting pollinating insects. If you look at the pesticide label, you will first see this front pack. If you peel back the front pack, for any of you that have not done this, or if you look more closely, you will see an EPA registration number. This indicates that the product has undergone an assessment and has been registered. But then as you peel back, you'll see use directions, directions for use, general use directions, directions that apply for any way that you use this product, as well as specific directions. Here you can see the directions for rose, ornamental, evergreens, and flowers. At the beginning of the label, there's another section called environmental hazards, and here you may see language specific to bees, very standardized language to warn applicators of pesticide products that might have high acute toxicity and long residual times. Since 2011, EPA has been requiring all registrants to do that full range of tests. And since any product after 2017 has gone through this risk assessment, And you can see what a new label will look like. Under environmental hazards, it will tell you, do not apply this product or allow it to drift to blooming crops or weeds while bees or other pollinating insects are foraging in a treated area. But it has this additional language that says you need to follow the label directions to minimize drift and reduce risk to these organisms. And so when you go into either specific or general use instructions, you will see additional information here. For example, this product can't be applied or shouldn't be made during bloom unless it's applied 2 hours prior to sunset until sunrise, or the temperature is below 50 Fahrenheit when bees are not expected to be flying. So this additional information is really rooted in the risk assessment process and all of those steps that you saw in the boxes and in the tiered risk assessment. Okay, we covered a lot. So just to sum up, the need to take into account the safety of bees emerged with the 1964 amendments to FIFRA, which put at the front environmental hazards as one of the things that need to be taken into account during registration. EPA had been assessing the risk of bees for many decades, but 2014 marks a real leap in the advancement of how we characterize risk of pesticides to bees. This means that new pesticides are evaluated using the tiered approach outlined in this talk, resulting in a more rigorous approach to weighing the risks and benefits of pesticides available on the US market. And as I mentioned, this is resulting in pesticide labels that have a much more close alignment with the series of tests and that whole risk assessment, tiered risk assessment that I described earlier. Again, all this material on understanding pesticide labels from this last section of my talk is covered in these infographic cards, which you can freely download from the NAPSI Pesticide Task Force website. Check our task force website for additional information on pesticide safety around pollinators. And with that, I want to thank a number of task force members for helping kind of put a lot of time into this talk. You know who you are. And if there are any questions, I'd be happy to answer them.
So, Anthony, we have 7 questions in the Q&A.
Okay.
And you can see them if you click on Q&A. Oh, 8 now.
Shall I take them?
Why don't you go ahead and take them, and I will answer them live as you have that opportunity.
Okay, fantastic. The first question is, what is the role of field studies or semi-field studies in regulatory process? Are all pesticides going through field studies in pollinators? I hope it's clear from the presentation, that might have been an early question, that in some cases, a tier 2 test may not be warranted. The risk is sufficiently characterized at tier 1 that a lab test on individual bees is sufficient. Tier 2 and tier 3 tests are when there's uncertainty at tier 1 or at previous tiers. That is the point at which that triggers a higher level study. The next question we have, can you clarify exactly what conditions will trigger higher tier analysis if the crop isn't bee attractive but near something else? How is this determined? Isn't there always some risk of off-site transport, which can include flowering vegetation? That is an excellent question. I've viewed some risk assessments. The one that I showed you earlier in the presentation, where off-site vegetation was considered, and I don't know the answer to this, and maybe perhaps there's somebody from EPA who is out there. We can trying to see if there's somebody who might be able to help. My sense is if it was at a time of year when there's a lot of flowering plants. Oh, I do see Tom Steger there. I'm going to see if Tom is available to, if he's here as a participant, but somebody able to bring Tom Steger out of the stack. He might be able to help us with that. Thank you for your question. My sense is if it was at a period of time when there's a lot of vegetative growth, but I don't actually know the answer to that. We may have some other people here as well, but let me go on to George's question. I'm hoping for some discussion of otherwise unregulated material like adjuvants, especially coated seed planting, runoff from the field to waterways, and the disposal of unused coated seeds. Thanks for that question, George. I'm not sure how much I can help with this question. The adjuvants, of course, are not regulated. They're not considered a pesticide product. And I know there's been a lot of concern about adjuvants in their own right having toxicity. And so this is not currently under the risk assessment. With coated seeds and runoff, again, this is a complicated issue because the pesticide application, as you know, is made to the seed, not its planting. And so this results in some complications, but it's also something that's kind of outside my scope. It's not my expertise. Oh, great. Tom, there was this question about off-target. I don't know if you heard it, this off-target. When are off-target effects considered?
Yeah, as Tom Seeger, off-target effects are routinely considered. As you had indicated in your presentation, EPA doesn't just evaluate effects to bees on field, but we also consider the extent to which bees may be foraging off-field, and we actually calculate the distance that the pesticide would move and still represent a risk to organisms foraging on flowering plants that are adjacent to the treated field. So the risk calculation also includes those distances. And the decision to move to higher tier studies is in large part predicated on whether risks can actually be mitigated. And if they can, after tier one, then these higher tier resource intensive studies are not called in. We try to reserve our efforts to where they are most needed and impactful.
Thank you, Tom. And if I could bother you for one more question, I just don't have the experience here in Oregon dealing with treated seeds. Am I correct in saying that when it comes to a treated seed, the label is for the application to the seed? And once, I see there's another question here about EECs for treated seed road of exposure. Those are treated in the risk assessment. Can you, if it's possible to?
Yeah, so EPA evaluates treated seed as the application rate in terms of the amount of product that is applied per acre. We consider that both in terms of how much would be subject to runoff into adjacent areas. That's quantified, and we qualitatively characterize what's referred to as dust off, which is the abrasion of treated seed coatings during the planting process. That represents a form of drift. It involves a number of factors, or it's influenced by a number of factors that would be difficult to predict how they're combining to influence the extent of dust off. It depends on the type of seed, the weather, the equipment that's being used. So we qualitatively characterize those risks, but in terms of runoff and exposure to areas adjacent to the field, those are characterized quantitatively.
I see we're at the top of the hour and there's more and more questions. I would recommend, I'm going to just type my email into the chat. The task force is really delighted to get your questions. Can I do that? Can I put it in the chat? Yeah, I can do that. I'm going to put my email in here. I would love, and I can get these, I believe I can get, here we go. I would love to, I can get the results of the chat as well. I'd love to bring them back to the task force. This has been really, thank you so much to task force members, and thank you to the Extension Foundation and to all of you for a lot of material, a lot of information. I really appreciate it.
Thank you so much, Anthony, for a really informative session, and we're happy to host anytime. Thank you for everyone who has been a part of today's session. Be sure to give us feedback because it will help us improve future sessions. Thank you again.
Bye.